we are going to start find the potential due to hollow metallic sphere. So a metallic sphere is hollow, means inside of the metallic sphere there is no electric charge, so all the charges lies outside of the surface of the metal. You can see this is the hollow metallic sphere of capital R, radius capital R. So we now have a task to find the electric potential at R greater than R, R equal to R, and R less than R. These are the three conditions. So as we know, so we are applying the Gauss's law. So close integration E dot ds equal q by epsilon naught. So now we consider a Gaussian surface at distance R, which is greater than capital R. So we consider a sphere or shell at distance capital R from the center. So the surface area will be 4 pi r square of this metallic shell. So here E into 4 pi r square equal q by epsilon naught. So q is the charge inside the sphere or the Gaussian surface, and q is nothing but the total charge in this metallic shell. So from here we can get E equal to q by 4 pi epsilon naught into r square. So it is the same electric field as due to the point charge of q presented at a distance r from that point. So now potential difference equal to V equal to integration of infinite to r E dot dr. So now we know the value of electric field at r greater than r, means radius of the metallic shell, is equal to q by 4 pi epsilon naught by r square. So just substituting the value of E over here in the equation of the integration. So over here we can take out q by 4 pi epsilon naught from outside the sphere. So we now have a integration minus q by 4 pi epsilon naught integrate from infinite to r dr by r square. So you can see after integration the value comes q into 4 pi epsilon naught into 1 by r minus 1 by infinite. So 1 by infinite is 0, so q by 4 pi epsilon naught into r. So this is the potential at a point at distance r from the center, where r is greater than the sphere radius of the metallic shell. So this is the electric potential outside the metallic charge shell. So similarly at r equal to r, we can draw the Gaussian surface. We can get E into 4 pi r square equal to q by epsilon naught. So E equal to q by 4 pi epsilon into r square. R is the radius of the metallic shell. So now we have to find the potential, the same formula, integration minus of integration of infinite to r E vector dot dr. Okay. So here the limit is from infinite to r. R is the radius of the metallic shell. So here we can do the integration. We can find the V equal to q by 4 pi epsilon naught into r. So this is the potential at the surface of the metallic shell. Now we come inside. So here inside, if we draw a Gaussian surface over here, this is the shell. Now we are drawing the Gaussian surface over here. So this is the Gaussian surface of radius r, and this is the metallic shell of radius r. So r is less than r. So now you can see over here that the charge enclosed by this surface, Gaussian surface, is 0. So q by epsilon naught is 0. So electric field inside this shell is 0. So the electric field always inside a shell is or a conducting shell or a metallic shell, charged shell, is equal to 0. So now we have to find the potential over here. So potential is nothing but a work done and bringing a unit positive charge from infinite to that point. So we are bringing the charge from infinite to distance r, where r is less than r. So now for r greater than the radius of the shell, we have the value of the electric field is q by 4 pi epsilon naught by r square. over here, q by 4 pi epsilon by r square. But inside the shell the electric field is 0. Okay, so at the point at the surface of the shell there is a discontinuity of the electric field function. So we are breaking the limit of the potential from infinite to r. Okay, sorry, over here. So infinite to radius of the shell or the surface of the metallic shell, and then again from the surface of the shell to inside of the shell at a distance r from the center. So this is nothing, just the electric potential at the surface of the shell, which is equal to q by 4 pi epsilon naught into r. Okay, q by 4 pi epsilon naught into r, and here the electric field inside the shell is 0. So the overall integration will also become 0, 0 dot dr equal 0. So potential inside the cell will become, or the metallic shell will become, q by 4 pi epsilon naught into r. So you can see here that the potential inside the shell is always a constant. It is not a function of the distance from the center of the shell. It is always a constant function. Okay, so here you can see the plot of the potential versus distance from the center of the metallic shell or a charged shell. So till the radius r, or till the surface of the shell, the potential is constant. The value is given by q by 4 pi epsilon into r. R is the radius of the metallic shell. But as we go after the at the boundary or just outside the shell, the potential becomes the function of the distance. So here the potential becomes q by 4 pi epsilon naught into r. So here the potential is inversely proportional to 1 by r. Okay, so r is a distance from the center of the shell. So it is nothing but the equation of a rectangular hyperbola. Okay, so the graph will at distance r or r greater than r is nothing but a rectangular hyperbola. It will go to infinite. At infinite, vi at infinite will equal to 0. Okay, so the function minimizes at infinite, the value of the potential is 0. So thank you. So this is the potential of a metallic shell. Okay, so thank you for today's lecture. Hope you will meet in the next lecture.